Welcome to CPE 350, chapters 5.1 to 5.3. In this section, we'll cover the shell balances for a transient conduction problem in one dimension. So our problem is going to be a rod of length L, a circular cross-section that's completely insulated, so there's no heat losses on that 2 pi r circumference interface. And at time equal to 0, the entire rod as it is at temperature T0. And then, instantaneously, we apply constant temperature sources or sinks at a temperature of T1 on either end of the rod. And this is true for any time greater than 0. So this is kind of like calculus where you had a 0 plus and a 0 minus. This is our 0 plus because it's any time just infinitesimally greater than time equal to 0. So that's the situation. And it's a transient problem because at time 0, when you apply those two temperature sources on either end, the temperature in the middle of the rod is going to start to slowly change as it warms up. We'll assume that T1 is greater than T0. Okay, so how do you model this? Start with an energy balance. In minus out plus net gen equals accumulation. In this instance, we don't have any generation term. It's just a solid metal conductor. So we'll neglect that. Net generation goes to 0. And we're going to give the expression for accumulation because in this case, it's a transient problem. So we're not at steady state. And the accumulation term is given by the material density of the conductor, the conduction volume, the heat capacity of the conductor, and the change in temperature. And your course notes will break this down if you're very curious about where this arises from. But you can kind of see that it makes sense just doing a dimensional analysis. And I love dimensional analyses because it just confirms to me that whatever I'm doing is likely to be correct because it has the right units. And so here I'm putting in the units for each of these terms. Heat capacity is joules per kilogram Kelvin. Sometimes we report it as joules per mole Kelvin, but you can easily transform between the two if you know the molecular weight of the species. And temperature is in units of Kelvin. All right, so Kelvin cancels out, kilograms, meters cubed. And so what we end up with is that this accumulation term is in units of joules, or just energy, which makes sense because we're doing an energy balance, so each of the terms should be energy. But that is our accumulation term. And one thing I'll point out is that whenever you see a heat capacity in a heat transfer problem, that's a good sign that the problem is transient because heat capacities do not arise in steady state problems. Heat capacity is kind of like a bucket that you have to fill up the heat capacity of the material before you can start to change the temperature. And so that only happens when the temperature is changing in time. All right, so if we write down our energy balance, here's our in term, here's our out term. These are, again, the heat fluxes at the positions x and x plus delta x. And what's different here is that we're going to multiply by a delta t, a change in time, a time increment. And the reason we're doing that is to put the entire units of this expression into joules rather than joules per second. When we were looking at steady state problems, we did our energy balance on the heat flow because it's steady state, so we're not having to worry about different time increments. In this case, we are actually just going to balance the energy because the heat flows are changing in time. And so that's what multiplying by that time increment does. It takes our joules per second and transforms it to a unit of joules. On the right-hand side, we've got our accumulation term. And what I've done is expand this delta t into a temperature at an increment time plus delta T minus the temperature at a time T. And that's the definition of a delta, right? Final minus initial, which is switched from the way we write our fluxes. We write our flux in minus out, and so it ends up being a flux at x minus a flux at x plus delta x. So it's a nuance, but that's why the t plus delta t term is the first one in this expression. Okay, so this is our energy balance. It has units of joules, and what we can do is take out the area from our two heat flux terms, and on the right hand side we can transform that volume into the volume of the differential shell. And again, this differential shell, it's not the full rod, it's an incremental unit with length delta x and area A along the rod. And that's important because heat is transferring in the x direction. But within that area, within this differential shell, when delta x is infinitesimally small, we expect the temperature in this to be constant at all positions. So all these different positions will have the same temperature, but that temperature is going to be changing in time. Hopefully that makes sense. So here's our full energy balance, and the next step is always to start dividing by things. So we see an area on both sides, and then we have our two differential units, delta t and delta x. So we're going to divide by both of those. And when we do that, the equation starts to look like a derivative. So we'll take a limit. We'll take the limit. We'll start with the limit as delta x goes to 0. And that, of course, gives us the negative derivative of heat flux as a function of x. The right-hand side of the equation is unaffected because there's no delta x term there. We divided through by that delta x in the previous step. So now we'll take the limit as delta t goes to 0. And the left-hand side in this case is unaffected. There's no delta t term there. But the right-hand side, well, that's clearly a derivative of temperature with respect to time. And so what you'll also notice is these are now partial derivatives, because we've got an x-coordinate derivative and a t-coordinate derivative, and our flux, as we know, is dependent upon temperature. So in the next step, we'll substitute in Fourier's law for that flux. So if we substitute in q equals negative k dt dx, we can simplify this expression. We'll pull our thermal conductivity out of the x derivative, and when we do that, we're making the assumption that k does not depend on spatial position, and that is almost always a good assumption. And this is our governing differential equation, and this is the most rigorous form for the problem we're solving. In many instances, we find that k, rho, and cp are either constant within the range of the problem, or if we combine them in a certain way, that value is roughly constant. And quantifying how constant it is an issue we can discuss in later sessions. But the way we define this constant is the thermal conductivity over the density over the heat capacity. And again, I'm just going to do a dimensional analysis because that is my big tool for understanding situations and expressions that I haven't seen before. And so if I do that, I can start canceling the units here. We get a meter squared in the numerator. The joules cancels with the joules of the watts, but we have a seconds in the denominator. And so the units of alpha, the thermal diffusivity, are meters squared per second. And it might be a little bit of a jog here, but you remember that diffusion constants are also given in units of meters squared per second. And when I say a diffusion constant, I mean for mass transfer diffusion. But interestingly, we can also model thermal diffusivity as a diffusion property because, well, it's stochastic, just like mass diffusion. Whether a particular amount of heat will transfer left or right, it's random. It depends on activation energies and the kinetics of the problem. So that is our thermal diffusivity. And if we plug that back into our governing differential equation, it simplifies to this much tidier form, which is the form that we'll be working with. So again, embedded in this expression is the assumption that alpha is relatively constant within the range of the problem that we're studying. And we can come back and challenge that presumption later on. But for the time being, this is the generic way of writing the heat transfer equation for this problem. Thank you. I'll see you for the next section where we start to break this down.